good afternoon to you. Can you see my screen okay?
Yeah, looks good.
Great. Well, it's great to be part of the Virtual Pipeline Summit focused on digital transformation. We at Hifi hope to provide some unique insights on providing value-added applications using high-fidelity fiber optic sensing with artificial intelligence and more specifically machine learning software capabilities. I'll start with just a little bit of background on Hifi, then we'll talk a little bit about fiber optic sensing on pipeline-specific examples. We'll talk about performance with high fidelity, deployment alternatives and examples, some approaches to machine learning, and then more importantly, we'll dive into a number of different application case study examples and evolve to one that we're most excited about in using the technology for flow monitoring. Specifically for Hifi, a little bit of background on us. We've been around for just over 10 years. We are a fiber optic sensing technology company, but all of our pedigree and experience is very much focused in the energy space. Danny mentioned that we're partly owned by Synovus, a big E&P company, and Enbridge, a very large pipeline company. So as a result, it's been our focus both on downhole oil and gas wells, but more recently, much more focus on pipeline and pipeline safety. We market a platform which we call High Fidelity Dynamic Sensing, or HDS, along with the control room software we call HDS Monitor. And really our focus is high quality data, sensing with very high signal to noise ratio to provide solutions from the perspective of pipeline safety. We started off by focusing on solving or trying to solve the problem of space and time with pipeline leak detection. We're now expanding this to detect more preventative type conditions prior to a leak. If left unattended, could turn into something worse like a leak. And we're now more evolving into machine learning to focus on more value-added applications that are more operational in nature as pipelines evolve through various stages of pipeline or digital transformation. The challenges that we've gone to try to solve are really space and time. Traditional pipeline safety and operations will use all kinds of different sensors and approaches, whether they be things like flow meter sensors using a mass balance system for leak detection, microphones, negative pressure wave monitors, periodic surveys, whether they be inline inspection tools like PIGs, manual inspections, or otherwise. The challenge with all of these is not being at the right place at the right time when you were looking for real-time event detection. And so unless we can get to 100% coverage across space and time, there's always going to be this challenge and doubt in operating our pipeline safety. And there can be much more in the way of digital solutions here that can help complement things in terms of these very conventional but best of practice safety methods that I've referenced here. So enter the world of fiber optic technology. I'm sure people have seen images like this where we show telecommunications fiber optics has been used in that sector for years to carry vast amounts of data. But we can also use a specialized version of that same technology that can be designed as a high fidelity sensor. And so if it is a sensor, what does it sense? We can actually define this as really changes of energy. It could be thermal energy, changes in temperature to very high resolution of delta temperature, 0.001 degrees Celsius. It could be acoustic energy, so sound on a fully distributed basis. It's a light wave-based acoustic microphone. And then kinetic energy, movement, vibration and strain down to micrometers of displacement. But providing these measurements on a fully distributed basis, so every centimeter of the sensor is active, and we're using the speed of light, we can help provide more of a solution to this whole challenge of space and time. This is a bit of a commercial slide. I apologize for that. I'll move on to the case studies after it. But Hifi used to use older conventional distributed sensing technologies, specifically that were used or designed around telecom fiber. But we found it lacked the performance and the distance required for pipelines. So we developed a next generation version of fiber optic monitoring, again, which we call HDS, or high fidelity distributed sensing. It is unique in that its performance is extremely high fidelity, multiple orders of magnitude higher on performance. It's integrated around acoustics, temperature, and vibration and strain, all with one sensing fiber, all with one system. And it is, again, optimized over very long distances. Now, there's many that believe that a sensor that is more sensitive will actually generate more false alarms. actually, and particularly if they are integrated with what they're measuring, rather than just one variable at a time, like say acoustics, higher fidelity or higher signal to noise ratio actually can enable more effective machine learning, which can actually eliminate false positives and support 100% accuracy and intelligent decision-making around preventative leak detection, a variety of other applications. As mentioned, we've recently launched our HDS sensing platform, as well as our HDS monitor platform, which is for the control rooms. It's a software that can support multiple facets of applications that are important in the payback analysis or business case, which we'll focus on further in this presentation. A little bit more description just on the technology. There's really three major components to what we do. One is, as I mentioned, the specialized fiber optic sensor, which is deployed with the pipe and is sensing for acoustics, temperature, and vibration and strain. As events or as data are picked up from that sensor in the field, which could be extremely long distances, we then have system hardware that provides the computational horsepower to process that significant amount of data. We have some pipelines that are pulling somewhere in the neighborhood of 10 to 12 terabytes of raw data a day that we need to process over very long distances. So we very much are in the buzzword of big data or edge analytics that are very important to what we do. And then finally, we very focused on the software algorithm side. So making meaning of that data, both through machine learning-based algorithms, as well as presenting that information on the control room software. And what's interesting is that the software can leverage the same physical sensing infrastructure in fiber optic cabling and hardware, but we can synthesize that same set of data for much more operational applications. And I'll go into some of those during the presentation. We often get a question around deployment. How do you deploy fiber optic sensors, which of course look very fragile, into an industrial environment like a pipeline right away? We literally have three deployment methods that we talk to: on the pipe, near the pipe, and actually internal or inside the pipe. Here's actually a couple of examples here of what we of course call on the pipe. We actually use an electrical conduit from a company called Durline, which we secure at the 12 o'clock position in this open cut environment. This is actually an example in Canada from the Trans Mountain Expansion Pipeline, which is one of the largest current construction projects of its kind at over 1,000 kilometers, and they have provided us approval to use this image. We can also do what we call near the pipe deployment, which can be appropriate where we just have the conduit with the fiber optic sensor down the middle of the right-of-way that might be able to support multiple pipes in that trench. We can also use micro-trenching of existing pipelines to be able to provide that same level of sensing capability and coverage across existing pipelines. Of course, we need to support trenchless methods as well, especially important if we're looking to tail on a large pipeline construction. What we do here is that same electrical conduit is connected to the pull head, usually in redundant forms, so that we can pull conduit along with the pipe as we do river crossings or large road crossings. It's not just horizontal directional drilling, which we're showing here, which is probably one of the more common trenchless methods, of course, but other methods like direct pipe, slip pipe, pipe and pipe, micro-tunneling are all important elements of the solution. And then finally, internal development, where, again, I mentioned retrofitting being very important, especially for high consequence areas that are typically going to be shorter, like an existing river crossing. We can support this through internal deployment, where the sensing fiber is first protected in like a stainless steel capillary tube and injected through a pack-off assembly, like in this image over here, and often actually a toe peg, which is in the image on the right, where we push and pull the line into place, and then we can actually monitor from the inside of the pipe within the flow of the pipe. Again, great for short sections where the pipeline operator is concerned about high consequence as a result of that. So beyond deployment, then, I wanted to get into a little bit about machine learning. There's a lot of talk, discussion. Mr. Vander Speck did a great job of defining some of these around AI and machine learning. But I thought we'd go to a different level here in terms of talking first about AI, which is really about creating program capabilities that can sense, reason, and act on a set of data, and ultimately become more efficient in the performance of various tasks. There's different versions of that. People are very familiar, of course, with more what we call narrow AI, examples like Alexa or Google Home, where we have Boolean logic and nested if-then analysis. which can be very predictable, although very generic in terms of it doesn't necessarily lend itself well to specialized or industrial applications. Machine learning, which is a subset, then takes a more strong AI approach and migrates to the ability to improve performance by adapting and making different decisions from similar data. And this can be then pushed forward into deep learning or reinforcement learning, as it's called. Now, some of the approaches that can be taken with machine learning is both supervised and unsupervised learning. So unsupervised learning really includes taking a massive clustering and dimensional reduction of data to be able to make meaning of a large data set. Supervised learning is a little bit different, where we're working with known inputs and outputs, and the rigor is really applied where there's a significant amount of classification and regression analysis provided in making meaning again of that data. At Hifi, what we do is we do supervised learning around leak detection. We have a very large leak database full of hundreds and hundreds of leak signatures in terms of data sets. And we can use a variety of classification and regression analysis as part of that, including support vectoring and classification, which is, again, very good for major or massive data sets in real time. Beyond leaks, we also have other operating conditions or anomalies where we'll use unsupervised learning, specifically around things like function fitting, where we attempt to predict a formula into a data set to estimate something else like flow potentially in the future. And then we also have what we call a non-leak event database, where we use supervised learning for things like security intrusions, construction activity, digging on a right-of-way, either by accident or potentially on purpose, geotechnical activities, areas that we can draw upon supervised learning for those events to be detected as well. Showing some of these case studies, this is an example where we actually can show leak detection, or in this case, rupture detection, by integrating acoustics and strain. You can see here we have a large rupture. The acoustics are on the bottom, where we're showing a very saturated set of acoustics across a number of frequencies. In other words, it's a very loud event. But we also correlate with that with strain on the pipe to be able to ensure that we don't have a false positive condition just because something was loud, but we actually are indeed correlating on actually having a leak condition. Now, in this case, a very large rupture isn't as difficult to detect as others that are pinhole leaks. This is an example where it's not that easy. These are an example down here on the lower right of frequency of a very busy field in West Texas, where we have pump jack activities, a lot of traffic of vehicles. We have an intersecting pipeline that is flowing. And if you were just focusing on acoustic monitoring, you might miss this very small pinhole simulated leak that was generated by the pipeline operator. However, at the exact same time, you can see we have strain on the pipe from two channels correlated with that exact location that allowed us to ensure that we're providing very accurate leak alarms without generating false positives. Now, beyond leak detection, which is, again, a big part of the presentation here, is things like geotechnical activities. We can actually detect earthquakes. This is an example where we detected an earthquake about 300 kilometers away, but the intensity rating was still about 3.0 at the location. This was in northern Montana. We were detecting this in southern Alberta, where we could still hear the acoustics of the earthquake, as well as feel the ground moving from the strain, both the earthquake event and an aftershock. This created a preventative shutdown situation on the pipeline, and while inspection did find major ground issues, the pipeline was thankfully undamaged. Actually, drilling into this location just a little bit more, it's very interesting. You'd actually see the fissure across the slope where the earthquake had generated this ground movement. We actually have two fibers, sensing fibers in this slope. One that's actually connected onto the pipe below the ground at around 3 meters. The other, which is actually above the pipe at about 1 meter. And we can use this to essentially differentiate ground movement from pipe movement. And in this case, the earthquake that I mentioned before, we were able to detect on both the pipe and the ground, both moving from the bottom of the hill to the top of the hill. And it's a very universal event in terms of we're picking up it on every channel broadly. Now, that's an example of a one-time event. What we can also provide is more cumulative level reporting, where, again, we're showing, say, 2 months of data here where the fiber that's buried with the pipe is on the bottom, relatively limited cumulative strain activity, which is great to see. But the ground fiber in both months is actually exhibiting relatively significant cumulative strain. And this was actually, interestingly, based on significant rainfall, meaning that the weight of saturated soil created strain on itself. We were able to, again, differentiate this type of activity. Other examples, you may have situations where we have a flow loop, like this example, where it's designed to address expansion and contraction of the pipe due to thermal changes and ground movement. You can actually see, again, the fiber optic deployment at the 12 o'clock position in the orange conduit. And we can provide, again, reporting here, not necessarily on real-time events, but cumulative level of strain, where we've got the pipeline distance across this axis. Here we actually have 30 days of data, so we're actually showing cumulative level strain over a month of data, both combined tension and compression here. And we can show this by segment, inclusive of, you see the red line here in terms of what is the normal baseline of strain that's normally exhibited on this pipeline. What's very, very interesting is that towards the end of the month at that expansion loop capability, we actually started to see significant amount of a cumulative level of strain here towards the back end of the month, which was alarm back more not to leak detection professionals, but instead integrity management professionals. So this is a great example of data that was generated by a system that was first designed for leak detection, but now provides other value-added data that in some cases are unknown to the operator and very much under a framework of digital transformation. Another quick example, pig detection and tracking. More operational, of course, in nature. We can detect pigs as they travel through the pipeline on the distributed sensor by picking out the acoustics on vibrations as pigs like this one scrape through the well joints and through pipe bends. So we can use this data to simply track that pig and indicate on an interface, say this pipeline kilometer post marker map, to show where the pig is in context of other locations along that. We can also use that to track sequential data. And that can actually show pig runs where we may have slowdowns here from the pig coming down the pipeline correlated to slowdown on flow. And then in cases, stoppages of that pig, which again are very valuable information to know from a pipeline operations perspective under a digital transformation. We can also provide then analysis on sequential pig runs in terms of does time, average strain, total strain from the pipe that was exhibited from the pig run, as well as time as well. And then finally, we can actually evolve this into other applications like flow monitoring. And so this is an example where we have output from the SCADA system on flow. You can actually see the set point changes on the flow from this period of time over this transmission pipeline. We can then use unsupervised learning and specifically function fitting to use the fiber optic sensor to create an energy propagation algorithm that allows us to plot an estimate of what the flow is as well. You can see they look very, very close. If I layer these right over top of each other, we can actually see almost 100% correlation. And so we're very excited about using this type of application around distributed fiber optic sensing and high fidelity, not just for leak detection, but other applications such as this in terms of flow monitoring that can assist with batch tracking, custody transfer, highlight flow anomalies, or even early set on cases of corrosion where we may see a pitting signature in the flow data. And this definitely represents another great value-added applications under the framework of digital pipeline transformation. Just quickly in closing, just a couple of illustrations here of a web-based control room software, human-machine interface that we use for event detection, event presentation, either on map-based schematics like this, and the ability to then provide event details in terms of acoustics. You can literally listen to events or flow in real time through the acoustic sensing capabilities of the high fidelity sensor. And then as additional details come in on various events, allowing analysts and operators to dive much deeper into the data and various image processing around illustrations of that data. So in summary, distributed fiber optic sensing is a great way to provide preventative pipeline leak detection, but as part of digital pipeline transformation, high fidelity sensing can be leveraged for much other deeper value-added applications that are more integrity related, whether they be peak detection, tracking analysis, real-time or cumulative strain, and other event detections, such as evolving that capability all the way to flow. We actually see a day when the deployment of the technology is justified in the business case for more operational-based applications, which then also provides direct leak detection as well. So I wanted to thank you for your time. Happy to answer any questions if we do have time. If we run out, I've included my contact information here. Feel free to email me with any additional questions you might have.
Thank you, Stephen. I think we are running a little short on time, but that was a very thought-provoking presentation, and we've had many questions. So thank you to everyone who's asked a question. I apologize that we can't get around them all, but why don't we start with Luis D'Angelo, who says, this technology allows the detection of illegal taps?
Absolutely. Great example. I talked about security intrusion database, and I said construction equipment that might be digging accidentally. It could be much more sinister than that. So illegal tapping in areas where that type of activity is alive and well, Mexico, Nigeria, Korea, we're very aware of those. So the ability to provide what we call security intrusion detection from illegal hot tapping is exactly the example that I was referencing.
Great, thank you. I also want to go to Stephen Edmondson's question, who says, is 100% coverage needed for pipelines, or is a risk-based model a better approach, focusing the sensing at high consequence areas?
It's a very, very good question. We have example operators that are, and I mentioned Trans Mountain expansion, they are deploying that technology tip to tail on 1,000 kilometers, so the full distributed coverage. We have other operators who are very focused just in those shorter high consequence areas, and we can deploy smaller systems that are 1,000, 2,000 meters that are just focused on that river crossing or that environmental zone that are more high consequence in nature. We can do both.
Okay, and if it can do river crossings, can it also be deployed on offshore pipelines as well?
Absolutely. We've done a lot of testing actually for offshore with subsea type of sensing where the sensor is, of course, underwater for offshore and nearshore type of applications.
Excellent. Thank you very much, Stephen. There's plenty more questions there on the app. I'm so sorry that we don't have time to read them all out. But Stephen's contact details are there, and I would encourage you to reach out to Stephen to learn more, to answer your questions.